In this demonstration, we're going to learn about faults. Faults form in response to plate tectonic motions, such as divergence and convergence and transform motions. If we begin with divergence, remembering that that means that the plates are moving apart, and we imagine now that we're looking at a cross-section of the Earth's crust. As I move my hands apart, the motion we actually generate is called normal fault motion. What we observe is that the foot wall moves upwards and the hanging wall moves downwards. If we now instead consider convergence, plates moving together, what happens now is that it's the hanging wall that rises and the foot wall that moves downwards as I move my hands towards one another. The first type of fault, when it is the foot wall that rises, is called a normal fault. It tells us we have plate divergence. The second type of fault, where it's the hanging wall that rises, is called a reverse fault. It tells us we have plate convergence. Now we also can get horizontal motions on faults. So if we imagine now we're looking at the Earth's surface from above and we have a fault, there are two possible motions we could observe, both of which would be horizontal. There can be a motion to the left, referred to as sinestral. There can be to the right, referred to as dextral. Sometimes we get more than one fault together, and a combination of faults can lead to really quite spectacular landscapes. I'm going to illustrate that now. With this little wooden model, I've got two faults on this model, both of which are normal faults. And what I'm going to do now is I'm going to move my plates apart, divergence. As I do so, the middle part sinks downwards along two normal faults. That middle part is referred to as a graben. The parts that have moved upwards relative to that graben that I'm holding in my hands are called horsts. I am currently standing on one of the most spectacular grabens in Sweden. The lovely flat surface I am standing on is the floor of a graben. But now if we look around us and we look up onto the hillside there, we can see a large ruined building called Brahahus. That ruined building is sitting on top of a horst, and that steep slope between myself and the building is a very large normal fault. So if we return to my model, Brahahus is here, I am standing here. So Brahahus is on the horst, I am on the graben. If we look further afield, we can see that this magnificent graben is the location of Vättern. The entire massive lake, Sweden's second largest lake, occupies a graben in the central part of Sweden. This graben is over 600 million years old, perhaps 700 or 800 million years. So let's take a closer look. I've come up now so that I'm standing right alongside the normal fault on the eastern side of the Vettern Graben. Let's just remind ourselves how a normal fault works. So it's produced by divergence, extension, and what happens is the footwall rises and the hanging wall sinks. So I'm standing with my foot on the hanging wall, and I'm resting my hand against the uplifted footwall of this absolutely massive fault. Motion on faults can be fairly smooth and continuous over time, moving at the rate that the plates are moving, centimeters per year. But it doesn't have to be smooth. Sometimes stress starts to build up. Motion stops, stress gets more and more and more and builds up over tens, hundreds, maybe even thousands of years. And then all that stress is released at once with a really sudden motion. Geologists call that an earthquake. And I thought I would demonstrate how that occurs. And because we're in Grena, I thought it appropriate to demonstrate with some nice Grena polka grease. And it's one of the original ones, so it's going to be nice red and white, very, very pleasing. So what you probably know with polka grease, if I bend it, I can bend it just a little bit, particularly if it's warm. What I'm actually doing is I'm applying stress and creating strain within this polka grease. If I carry on forcing it and bending it, at some point the stress becomes too much and the strain is released. That's the earthquake. So sudden motion along a fault surface breaks up the rock in a similar manner to you just observe that polka grease being broken. And you can sometimes, when you approach a fault surface, find small fragments of rock still embedded in that surface. And that's telling us about an earthquake that once occurred along this fault. We call that breccia, and there's some really good examples on this surface. I want to come up here a little bit because it's really, really nice up here. Yeah, if we see here, we can see there's lots and lots of angular fragments of the host rock embedded, so I can't get them off, embedded into the surface. This is a breccia, it's a fault breccia, and finding these in the geological record tells us about where there were ancient faults, such as this one, over 600 million years old. Wow, it's a long way down. I'm now standing on the uplifted footwall of that normal fault. So let's just remind ourselves what that means. Here we've got our normal fault. The footwall rises, the hanging wall moves downwards. So now I'm standing on top of that uplifted footwall. And I'm looking out across the down-thrown hanging wall. And in the foreground, I see the village of Grena, the harbour, and then Vättern, Sweden's second largest lake. Looking out into Vättern, we see the island of Visingsö. Looks like it's more than halfway across. And we can just make out the far side. This massive lake is occupying a graben. Let me remind you how that formed. That formed due to plate divergence causing extension. So Vättern would be occupying the graben between the two horsts that I'm holding with my fingers. We're standing here on top of the eastern horst. Far across on the other side of Vättern will be the western horst. Thank you for joining us at Vättern, Sweden.